We're going to be looking at this video about the equilibrium of a rigid body. Now, a rigid body, first of all, a rigid body is an object that possesses notable dimensions in contrast to a particle. So a particle basically had no size, it was just tiny little things, so that it didn't matter where you touched it, it didn't have a turning effect. But when we apply a force or forces to a rigid body, it can experience a turning effect. And very importantly, where you apply the force makes a difference to the turning effect. So the moment of a force measures a turning effect of a rigid body, and it is measured from a selected point, and this point could be any point at all on the object or outside the object. You have to decide where that point is, and it is defined as a force multiplied by the perpendicular distance to our chosen point. And then this is our very important bit here. This is our equation. It says the moment of a force equals a force times a perpendicular distance. So that's a perpendicular distance from your point about which you're taking moments, or moment of a force is force times the distance. Okay, I'm going to pause the video. I'm going to do a diagram of a spanner, something we are familiar with. Moments are something you naturally understand. It just gets a wee bit more complicated when we apply mathematics to it. Okay, here we have a very bad drawing of a spanner trying to loosen a bolt. So you've got A, B and C. These are your options of where you want to apply a force. Now, if you apply the force of B, it would definitely have some sort of turning effect. Here is your pivot here. Your pivot would be here. That's where your bolt is. So B would definitely have a turning effect. But what you would know, and you would know this sort of naturally, when you picked up a spanner, if you applied the same force, and that's very important, if you applied the same force as you did at B, it would have a much greater turning effect and when you applied the force through A. Okay. Also, if you applied a force vertically down here at C, it would have absolutely no turning effect. And the reason for that is its perpendicular distance from the pivot is 0, because it's actually, if I continue that line on down, it was acting on through the pivot. Okay, so your turning effect is a force times a perpendicular distance. So that's why the force acting through A has the greatest perpendicular distance, so it would have the greatest turning effect. And that is it. Okay, so back to our notes. First of all, the units of moments are Newton meters. Remember what that is. It's force times distance. So force is in newtons, distance in meters, and the force must be in newtons and the distance must be in meters. A moment is a vector quantity, so it has both size and direction. So we refer to the direction as either clockwise, CW, or anticlockwise, ACW. And we're just going to look at a couple of examples now of how we go about doing this. This question, it tells you the point about which you want to take moments. It says calculate the moment of the force from O in the diagrams below. Or I could have said calculate the moment of the forces about O, but how we do this is the same way. So what I'm going to do is I'm just going to say I've got my point O, and I'm going to take moments. So that's a wee bit blurry. So I've got my point O, and I'm saying I'm taking moments about it. Now you can see my arrow is going anti-clockwise, against the way the direction of the hands of the clock go. If I do that, my force is 1.4, and the perpendicular distance is 1.21. And if you do that, you get 1.694, and that's going to be Newton meters, and that was anti-clockwise. And that's it. Okay, the next example confuses people a wee bit. So in your next example, we're going to go clockwise this time. Take moments clockwise about O, and my force is 15. That was my force, and my perpendicular distance is 3.67. And you just do it on your calculator, and you get 55.05 Newton meters, and that's going to be clockwise this time. Next one, again, it's going to be going anti-clockwise overall, so we're going to take our moment anti-clockwise about O. The distance of your force from the point, the perpendicular distance is 1.5 meters, but this force is not strictly going perpendicular, so you've got to force it to be going perpendicular. So to force that going perpendicular, just do a dash line going up here. So it's going to be, I'll get rid of that a wee second, it's going to be 12 newtons times sine 60 to pull it perpendicular, and then we'll multiply by our perpendicular distance, which was 1.5, and then if you did that on your calculator, it will give you a perfect answer of 9 root 3, which works out to be 15.59 Newton meters, and that was going to be anti-clockwise. Okay, next bit says for a rigid body to be in equilibrium, we require two conditions to be met. So first of all, the resultant force in any direction must be zero, i.e. the forces up equal to forces down, or the forces left equal to forces right. And also, the algebraic sum of the moments from any point about any point is zero. So if it's in equilibrium, if you resolve vertically, your overall force going vertically is zero. Resolve horizontally, your overall force horizontally is zero. And also, the algebraic sum of moments about any point is zero. So if you take moments about, say, the end point, maybe A, take moments, it's going to work out to be zero. Maybe you take moments about the middle of the object, it's going to work out to be zero. Take moments about another point, it's going to work out to be zero. But you only have to pick one of those points. So it can be, you could be doing these examples very differently from me, and you still would be getting your full marks in an exam. Okay, notice the next wee bit says the second point is called the principle of moments, and is commonly rephrased as the clockwise moment equals the anti-clockwise moment. Okay, and that's basically it. So the overall clockwise moment equals the overall anti-clockwise, and then overall that means there will be no turning effect. Okay, going to look at a couple of examples here. 1, 2, 3, 4 examples, and then we have another couple of sort of more special examples after that. It says in this first one, it says, in the examples below, calculate the sum of the moments and hence determine if the rigid body is in equilibrium. Now folks, without doing anything here, I can tell you this is not an equilibrium, because you've got a 6 going up here and you've an 8 going down here. So your overall force is not going to up vertically is not going to be zero, so it's definitely not going to be an equilibrium. So we're going to take moments and see what's going on. So I'm going to take moments about O, and I'm going anti-clockwise about O. Now this 8 is going anti-clockwise, so it's 8 times, and it's going to be 0.75. It's a perpendicular distance. Remember, I get that in meters. And you've also got 6, which is going relative to O, would be going anti-clockwise. So also it's a plus sign, 6 times 1. And if you do that on your calculator, you'll have 12 Newton meters, and it's going to be anti-clockwise. And that's it. So definitely not in equilibrium. Okay, next one. Again, if you resolve vertically, you're going to have 3.5 newtons going downwards, but we need to see, because it's a rigid body, we need to see what the moments are. I'm going to take clockwise moment this time. So, and again, take moments about O. And I'm going to say in this one, I'm going to have my 3 is going clockwise, and its distance is 0.3 meters. Plus, I have 0.5 newtons, and its distance is going to be 30 centimeters plus 1.4 meters is going to be 0.3 meters plus 1.4 meters. That's going to be 1.7. And again, if you do that on your calculator, what you'll get is 1.75, and that's going to be Newton meters, and that was clockwise this time. Okay, part C. Again, we'll just take moments about O. Just on that, folks, we could be doing this. We could be adding in a point A and taking moments about A, or a point B here and doing it, but because I've got the O written on, it's easier just to use the O, but you could do it in any way that you want. Okay, if you take moments about O, first of all, you've got this 5, and its distance is 0.25. Then going against that, you've got this 9, because it would be going anti-clockwise, and its perpendicular distance would be 105 centimeters, which is 1.05. And then if you have a look at this one, and I know I made a mistake on this one when I did this myself, this one is going clockwise, so it's 4, and its perpendicular distance, and I had added these incorrectly, it was 25, and 80 is 105, plus 65 is 107 centimeters, or 1.7 meters. Fire that into your calculator, and what it actually gives you is minus 1.4, So it's minus 1.4 clockwise, which is equal to positive 1.4 Newton meters brackets anti-clockwise, and that's it. Okay, our last one of this type, and we don't have an O here. I would put the O just on the end, so I'll label this as O, and then I'll take moments about O. Haven't a clue whether this one's going to be going clockwise or anti-clockwise, but if we do balance up in this one, if we resolve vertically, it's looking more likely that it's going to be balanced, because resolve vertically, you've got going upwards, you've got 5 minus 7.5 plus 2.5, which equals 0 newtons. So your resultant is 0 going vertically. It was the same in the last one, but it wasn't an equilibrium in the last one. But let's have a look at see about this one. So if we do first of all, what is the turning effect of this 5 newtons, which is going through our point about which we're taking moments? Okay, if you think about a seesaw, if you sit here, so if you sit here on your seesaw, your weight is acting down and you're a perpendicular distance about the pivot. If you had moved in a wee bit and you'd sat here, your weight hasn't increased, but your distance is less, so you do not have as great a turning effect. But if you move in again and you're sitting right on the pivot, there we go. If you're sitting right on your pivot, doesn't matter what size you are, you will have no turning effect because you're acting right through the pivot. So it is the same idea here. So if we've got here we've got our force is acting through a turning effect, so it has force is acting through a pivot, so it has no turning effect. So the only two things we have to consider is 7.5 and then this 2.5, but notice they're going in the opposite directions. So I'm going to take clockwise moments. So clockwise, I'm going to have this 7.5 and its perpendicular distance is 3. Then anti-clockwise, I'll have 2.5, its perpendicular distance is 9. So if you do that, you'll get 0 Newton meters. And so we're just going to say, therefore, in this case, we've resolved vertically and there's no resultant force, and we've taken moments, and your body is in equilibrium. Okay, this is our last bit for this video. It says, when we take moments about a point, any force acting through that point contribute nothing towards the overall sum of the moments. So just like we've seen in the last one, when dealing with multiple unknowns, we can choose to take moments about a point that cleverly eliminates an unknown for us. In this module, all rigid bodies will be a rod, a beam or a plank, which will be suspended on one or two pivots or held by strings, and we'll see this. So notes, if a plank or beam or rod is said to be uniform, that means the weight acts directly through the middle of the body. So a uniform object basically is balanced evenly. So its weight is evenly distributed, which means that the center of mass, or the weight, acts through the very center of the body. If it is said to be non-uniform, the weight acts through a designated point, which is not the middle. When a rigid body is in contact with a pivot, Newton's third law applies, and there's a reaction force. That is very important, that last point, and we will be seeing that in this example. Okay, uniform rod AB of mass 13 kilograms rests in equilibrium, which means on two pivots, as shown below at C and D. Find the reactions at the two pivots. So there's only two things that you can do in solving an equilibrium problem. First one is resolving vertically, and the second one is taking moments about a point. You can take moments about as many points as you want, but there are only two things that you can possibly do. So if you're in an exam, you think, you look at a question, you panic, you think, I don't know how I'm going to get to the answer. You can still just resolve vertically, and you can take moments about some point. There's the only two things. So if you just do that, 9 times out of 10, you will get to the answer. You will figure out what is going on. Okay, so let's look at this question again. Uniform rod AB of mass 13 kilograms rests in equilibrium on two pivots as shown below at C. And D, find the reactions of the two pivots. Okay, first of all, you notice that in case we had to draw this diagram ourselves or add things to it, this 130 newtons is basically that's our 13 times our G, so that's the weight of the plank. Its mass was 13, acceleration due to gravity G is 10, so that's where that 130 comes from. It's uniform, so you can see the distance from this end is 3.5 and the distance from this end is also 3.5, so that's why it's acting through the center. First thing I'm going to do is resolve vertically. Forces up are X and Y, force down 130. That's an unknown with equation with two unknowns, call that equation 1. Then I'm going to take moment about any point. Now it said in notes that you could take moments about any point that you want. It also said if you take moments about a point, if there's a force acting through a point which you're taking moments, it will have no turning effect. So sensible thing would be for me to either take moments here or to take moments here. Because if I take moments on this one, if I take moments on this one, my X has no turning effect. If I take moments on this one, my Y has no turning effect. So first of all, first thing I'm going to do is take moments about C. So taking moments about C, I have got clockwise, I've got 130 newtons, which is 2.5, and that equals anti-clockwise, and my anti-clockwise force is Y times 5.5. So I could have written that a wee bit different. I'll just say that's my clockwise is equal to anti-clockwise, and then if we just work that out, you're going to have 325 is equal to 5.5 Y, and then a wee bit of working out again, that means your Y is equal to 325 divided by 5.5, which works out your Y to be 59 and 1/11, and that's going to be newtons. So that means your X is going to be equal to, putting that back into equation 1, it's going to be 130 minus your 59 and 1/11, which means your X works out to be, and it's going to be 70 and 10/11ths, and that is going to be newtons. Okay, can we just go back and have a look at this example just to talk a wee bit more about the reactions at these pivots. Now here you can see our plank is touching, our rod, whatever it is touching this surface, this pivot, which means that's why there's that normal reaction. Likewise, it is touching here, so this is one of our Newton's laws. If there's a force, if you're in contact, there's going to be an equal and opposite force, so that's why there's this Newton's laws. We will see in later videos what happens if something begins to tilt, what happens to these normal reactions. Last example says a non-uniform plank of weight 75 newtons is held in equilibrium in a horizontal position by two cables, as shown in the diagram below. Find the tension in the cables. So it's non-uniform. They've drawn the weight is here. They have shown you where the weight is, and the weight was 75, not the mass, so weight of 75 going down. And then you've got two different cables. So if you have two different cables, their tensions are going to be different. So you can see they're called T1 and T2. So to do this, we're just going to, and first of all I'm going to mark on, I'm going to call this point A, I'm going to call this point B, I'm going to call this point C, and I'm going to call this point D. And if we resolve vertically, your force up is T1 plus T2, and that equals 75 newtons, which is going down, call that equation 1. And then if we take moments, you can take moments about A, B, C, or D, and it doesn't really matter which one you use. You'll get to the answer. You'll maybe get, but if you take moments about A or D in this example, you'll get an equation with two unknowns. So it's easier if you take moments about either B or C, because that eliminates one of the unknowns straight away. So I have just picked B here to make life easier. So if I take moments about B, I'm just going to say clockwise is equal to anti-clockwise. So my clockwise moment would be 75, and that's 1 meter away. My anti-clockwise moment would be T1, and it is 1.5 meters away. So we'll just go on with that and see what we get. So that means 75 is equal to 1.5 times t1, which means a wee bit of working out, 75 divided by 1.5 is equal to t1. My t1 works out nicely to be 50 newtons. And then that means your t2 is just equal to 75 minus 50. Your t2 works out to be 25 newtons. And that is us done for this video. So basically, if you've got an equilibrium question, resolve vertically, and the forces up will be equal to forces down. And if you take moments about any point, your clockwise will be equal to your anti-clockwise. And generally, there's an easier point to take moments about, so it removes one of your unknowns.